In this video, we're going to look at another very specialized type of noise measurement that we're going to do over and over and over again. We're going to look at noise on a victim line that is synchronous with the noise on an aggressor. And to set up an example, we're going to use an Arduino to generate a repetitive digital signal. That's going to be the aggressor signal. And we're going to look at that aggressor signal. We're going to use that to trigger the scope. And then while the scope is triggered with the aggressor signal, we're going to use channel 2 to measure the voltage noise on something else. And in this case, we're actually going to look at the voltage noise on the power rail that is synchronous with the noise on the aggressor signal. And the coupling mechanism, where that noise comes from, is related to that current transient. So when that signal on the Arduino switches and we get that dI/dt, that large change in current on the edge, that large change in current on the edge coming from the power rail is going to generate some power rail noise on the power rail that is synchronous with the digital signal on the Arduino. And so we're going to set up the system. We're going to look at the measurement on channel 1, that's the aggressor. We're looking at the measurement on channel 2, that is the victim. And then we're going to adjust the scales in order to see that. This is an incredibly powerful technique we're going to use over and over again when we're looking for noise that's correlated between an aggressor and a victim. There may be other sources of noise on the victim line, but we want to focus on the noise generated by the aggressor synchronous with the aggressor. Let's take a look at the setup. Here's our measurement setup. We're going to power the Arduino board from the 9-volt rail, and we're going to plug in the USB port so that number one, we have a ground connection between the ground on the board and the ground on the Analog Discovery 2. That means we won't have a large common voltage difference and we won't have the artifact of that noise. And we're also going to program the Arduino to generate a square wave. We're going to use pin 13 because it's really convenient and it's next to a ground pin. And we're going to use on pin 13 a simple digital signal that's switching off and on with a millisecond on, a millisecond off, so about 500 hertz. That's going to be our periodic signal that we're going to use to generate the noise. And that's going to be our aggressor signal. And so we want to be able to measure that. And we're going to connect a couple things into it. We're going to, as we will see, one of the ways that that signal generates noise on the power rail is when we have large current switching. And so we want to switch large currents. And the way we're going to do that is have the output pin of the Arduino drive current through an LED. And the combination of the output resistance on the driver on the 328 microcontroller, the output resistance through that LED is what regulates how much current comes through. And I've done measurements before, and it's about 50 milliamps of current is what we're going to be drawing from the power rail. While it's set up here, let's take a quick look at the measurement of that signal coming off of that pin. And the way we have to do that is, because we have the female pins on the 82, we need a little gender changer. And so I've got a little connector here with a bunch of pins on it, and we will connect it. And so now we have a connection for the signal pin. We have the two ground pins over here, and we'll take advantage of those. So let's do our connections. So +1 channel is going to be the aggressor signal. That's this guy here. And the -1 of the channel is ground. So I need a ground connection, and the nearest ground connection is the one that is way over here. And so we'll use the ground connection over here. And now, again, we're hacking this system up pretty quickly. We're going to have a lot of crosstalk between these wires. We may see that, but we're going to pay attention to any noise from any source synchronous with the aggressor. So let's just take a look at the aggressor signal. Here's that signal on channel 1 that we're measuring. Sure enough, it's a 5-volt signal, 0 to 5 volts. It's the output pin. And you can see, let's see, we're triggering on the falling edge. Let's trigger on the rising edge. We're going to want to go back and forth between the two. Hey, let's see, it's a half a millisecond a division. So it is 2 divisions on, that's 1 millisecond on, 2 divisions off, 1 millisecond off. So sure enough, there's our 500 hertz. Beautiful looking signal. That's our aggressor. Let's take a look at the noise on the power rail with just this aggressor driving. Not a lot of current is being switched right now, so we wouldn't expect necessarily a lot of noise. We want to measure the noise on the 5-volt rail on the board, and we can make the connection over here for the 5-volt rail. So we've got our connection for the aggressor, that's channel 1. We're going to use channel 2 to measure the victim, and in this case the victim is the 5-volt rail. So we're going to connect up. 2 plus is going to be the 5-volt rail, and 2 minus is going to be ground. So we're looking at the voltage difference between the 5-volt rail and ground locally on the Arduino board. So we've got it connected up. We're looking at the channel 1 is the aggressor signal. Channel 2 is the 5-volt rail. Now normally it should be just 5 volts, right? Let's take a look and see what that is. Here's channel 1. Now we're going to turn on channel 2. And here is channel 2. And you can see, okay, channel 2, the vertical scale here, 50 millivolts of division. We've already got it offset minus 5 volts. Wow, not much noise. And if we zoom out a little bit more, here's 10 millivolts of division. Now we can see, wow, you know what? There is some high frequency noise, but the low frequency noise, not much. Let's see there's a tiny little bit of noise over here. What we care about is how much noise is synchronous with the edge, either turning on or turning off. And you can see there's clearly some high frequency noise synchronous with the edge. So we're always going to trigger on channel 1. That's the aggressor. Whenever the scope triggers on channel 1, it's always going to simultaneously trigger channel 2 as well and display what's on channel 2. So we're triggering on the edge on channel 1. Let's zoom in on the behavior on channel 2 at that point. So we're going to zoom in. Here we are. Oh my gosh. And here's some more. And now you see that there is some noise that's happening right at the same time the edge is turning on. Let's zoom out some more. Wow. And here we are at 1 microsecond division. So when that edge switches, we see this additional noise that switches as well. Now, there's a separate question about why do we have the signature? Why does it look that way? Right now, we're looking at just what is the noise synchronous with the aggressor turning on. This is the victim line. In this case, the power rail is the victim line, and here's the noise synchronous with that. And you can see on this scale, we're talking about maybe 20 to 30 millivolts. That's about 50 millivolts peak to peak. Not very much at all. Whenever we look at the switching noise, that is noise on the victim synchronous with another aggressor switching, we always want to look at not only when the aggressor is turning on from low to high, the rising edge, but also the falling edge. What's the noise on the victim line, the power rail, when there's a falling edge? Well, let's turn on our trigger level to the falling edge. And you can see they're just about the same, maybe a tiny bit more noise. What the origin of this noise is, different question. We're going to address that later. This is just measuring that noise. And in fact, some of this is probably because I have these big floppy wires going from the measurement scope to the Arduino and all around it. So I probably have some noise picked up in just the wires, and we'll see the impact of that in a little bit and how we get around that problem. If we ever worry about the wires that do the interconnect because they're not transparent, that's when it's time to switch to the 10X probe, and we'll do that in a later video. Let's go back to the rising edge, and now we're going to make more aggressor noise. While that switches and turns on, now we're going to drive a lot of current, and we're going to do that by plugging an LED between pin 13 and ground, and that will draw a lot more current. Now, exactly how much current, you have to do other measurements and experiments to determine that, but I've done that in the past. It's about 50 milliamps. So we're going to turn on, when the aggressor turns on, we're going to turn on about 50 milliamps of current as well. Let's take a look at that setup. Here's our system, and now between pin 13 coming out and ground, we're going to go ahead and add an LED, and when it flashes, that says there's current going through it, and we're going to get about 50 milliamps of current. Let's connect it in. Wow, it's pretty bright. In fact, it's so bright, it's kind of saturating the camera here, so it's on a lot, 50 milliamps. let's take a look at the aggressor signal, and let's take a look at the victim signal as well. So here is the aggressor signal, and let's zoom out so we can see the whole thing. Remember, we're on about 2 milliseconds a period, so we'll get a 1 millisecond a division. Hey, there it is. But wait, we were getting 5 volts before. We're only getting, about 2 volts now. That's because we're looking at the voltage across the LED. This is the forward voltage drop of the LED when he's got about 50 milliamps of current going. So it's nothing, 50 milliamps, nothing, 50 milliamps. Now, let's take a look at the noise on the victim line, synchronous with that 50 milliamps of current switching. And to do that, we're going to turn on channel 2, which is connected to the 5-volt rail. And there we're, oh my gosh, there's a lot more noise now than we had before. And let's take a look at that noise signature on the 5-volt rail. So let's zoom out. Again, we're triggering on the rising edge. Here we are at 100 microseconds a division. Here we are at 10 microseconds a division. Very different signature of this noise. And we're talking about, let's see, it turns on, so we have a large DIDT in the positive direction. There's a voltage drop on the power rail that we're measuring of about minus 30 millivolts. If we were to turn off that current, if we look at the falling edge, when the DIDT is in the negative direction, what's going to happen to the voltage noise, do you think? Well, I think it's going to change polarity because I think it's inductive crosstalk. So we're going to go to the falling edge, and sure enough, there it is. Now, sometimes we'd like to compare the voltage noise in one case with another case. The waveform that we see in one situation, the waveform in another situation. And here's how we can do that really simply. Let's go back to the rising edge. This waveform, this is the signature of the noise that we see on the victim line, the power rail. We'd like to save this as a reference so we can compare it. And here's how we're going to do that. What we want to add is a copy of channel 2 that we can keep on the screen and compare it to other measurements. So we come over here to add a channel. It's a reference channel from channel 2. We click and it's there. A little hard to see. It's kind of superimposed on the real-time measurement. And so let's move that up. Now you'll notice we have a little cursor here. It's a gray color. We have a little cursor here. Here's that reference. That's the measurement that we took of channel 2 at that instant of time. And of course, we're still seeing the live measurement. If I unplug that LED so I don't have the 50 milliamps of current draw, let's see what that noise is compared to what I'm measuring now. Here's that LED. I'm going to unplug it. So here we're unplugging it in real time. Wow, look what happened to the noise. Completely different noise signature when I did that. And in this way, we can do a simple comparison. Now I'm going to move the reference on top of this signal. So I'm going to grab that caret and I'm just going to drag it down and do it again. So here they are superimposed. And you can see all this noise is from the current changing. Now again, we're not saying exactly where that current is coming from, or we're not saying where that victim noise is coming from, but we're just saying that is the victim noise synchronous with the aggressor signal. Let's plug in our LED. Let's get some more current. So we got that large current going. We can see really good consistency test. We're getting a reproducible measurement of the switching noise. Let's see what the noise looks like when we go from a high to a low. So we're going to change the rising edge to falling edge, and there's the falling edge. And now you can see very clearly comparing the switching noise on the power rail. We call it switching noise because it is synchronous with the aggressor switching. It's happening on the edge. It's synchronous with the aggressor. It's synchronous when the aggressor switches its state, in this case switching current. And you can see that when it goes from high to low, we get a positive going signal. When it goes from low to high, we get a negative going signal. This is a technique we're going to use over and over again in order to measure noise on a victim that is synchronous with an aggressor signal. And that distinguishes the noise on the victim line from other random noise. You can see there's a lot of other noise on the victim line as well, but none of that is correlated with the switching on the aggressor. And generally we'll find it's switching noise that is the largest amount of noise in the system, and that's why we'd like to be able to measure the switching noise from an aggressor switching. And that's why we'd like to be able to measure how much of the noise on the victim line is due to the switching of the aggressor signal.